Hello there, and welcome to the Science for Sleep channel, a quiet place where curiosity softens and the mind is free to slow down. Tonight, we drift gently into the ancient and extraordinary world of geology, into the deep memory of our planet written patiently and permanently in stone. Long before stars were named by human voices, long before oceans were given boundaries or maps, the Earth was already alive, endlessly reshaping itself in silence. In that vast, distant past, mountains slowly rose skyward only to crumble again, ground down grain by wind, water, and time. Entire seas vanished from the surface of the planet, leaving behind salt and stone, only to return millions of years later in different forms and different places. Continents themselves wandered across glowing oceans of molten rock, drifting like immense rafts through a restless, fiery world still settling into its shape. The ground beneath you is ancient beyond imagination, older than memory, older than language itself. Every surface you touch has lived through ages measured not in years, but in eons. And yet, despite this immense age, the Earth is not finished. It is still moving, still breathing, still quietly changing beneath your feet. This is the story of geology, a story written slowly, patiently, without urgency. A story of fire and water, of creation and collapse, of destruction followed by renewal. It is a story of beauty that takes millions of years to unfold, where nothing happens quickly and nothing lasts forever. Beneath every step you take, within every pebble and every grain of sand, there are whispers of ancient volcanoes, slow-moving glaciers, drifting continents, and even stars that burned out long before life ever appeared on Earth. If you enjoy these quiet journeys through deep time, you are gently invited to like, subscribe, or share a thought below. It helps other curious, sleepy minds find their way here as well, one soul at a time. For now, simply breathe, let your shoulders relax, let your eyes grow heavy, and allow the ancient Earth to cradle your thoughts as we begin. Earth's crust is far thinner than most people imagine. If you could shrink the entire planet down to the size of an apple, the crust, the solid outer shell where all life exists, would be no thicker than the apple's delicate skin. This idea can feel almost impossible to believe, yet it is entirely true. The continents and the ocean floors together form a layer that, on average, extends only about 30 kilometers deep beneath land, and less than 10 kilometers beneath the sea. Everything familiar to us exists within this fragile outer skin. Beneath it lies the mantle, a vast and powerful region of intensely hot rock that makes up most of Earth's volume and mass. Though solid, the mantle behaves over long spans of time like an unimaginably slow-moving liquid, flowing silently beneath the crust. The crust floats on this mantle like a collection of fragile rafts, drifting on hidden molten currents and carried slowly by the forces of plate tectonics. Mountains, valleys, and deep ocean trenches are merely tiny ripples on the surface of an enormous sphere of stone. Everything we know, every forest, every city, every ocean, every civilization that has ever existed, rests on a layer so thin it almost disappears when compared to the scale of the planet itself. Granite, one of the most familiar and enduring rocks on Earth, once flowed like molten rivers deep underground. Long before it hardened into the rugged stone we see today, granite was alive with heat and movement. Deep within the Earth's crust, molten magma gathered in hidden chambers, shifting slowly like glowing rivers of fire. Over millions of years, this magma cooled and crystallized, forming the speckled rock that now shapes the cores of mountains. Each grain of quartz and feldspar once shimmered in a molten glow before solidifying forever. When you run your fingers across granite, you are touching the frozen remains of that ancient flow, locked in time. Many of the world's great landscapes, from towering cliffs to ancient highlands, were shaped by granite rising silently and solidifying far below the surface. Granite holds within it the patience of the planet itself, a reminder that what appears solid and unchanging today was once fluid, glowing, and alive under unimaginable pressure. Diamonds tell an even more dramatic story of transformation. Most diamonds take billions of years to form deep within the mantle, born from carbon crushed and heated beyond imagination. But nature does not always move slowly. Under the most extreme pressures, carbon can rearrange itself into diamond almost instantly in what could be called a geological heartbeat. These sudden transformations occur miles beneath the surface, where temperatures exceed molten metal and pressures surpass anything humans can maintain. When volcanic eruptions carry these gems upward through narrow pipes of rock, known as kimberlites, they bring with them messages from the depths of Earth's creation. Every diamond you see, no matter how small, once existed in darkness and heat fierce enough to melt steel. Each crystal captures a moment when ordinary carbon became extraordinary, a perfect record of transformation shaped by pressure, time, and chance. Mountains may appear eternal and unmoving, but they are alive with motion. Deep beneath the surface, tectonic plates push and collide, forcing rock upward inch by inch. In the Himalayas and parts of the Andes, this slow collision is still lifting peaks today, at a pace faster than your fingernails grow. What feels solid and permanent is actually part of an endless cycle of uplift and erosion. Wind, water, and ice patiently tear mountains down grain by grain, while forces deep below rebuild them over millions of years. A mountain may seem motionless, but if you could speed up time, you would see it breathe, swelling upward as continents collide. The stone beneath your feet may once have rested on the ocean floor, carried skyward over vast epochs. These giants remind us that Earth is never truly still, but always reshaping itself, even as we sleep. Entire continents float like immense rafts on a hidden sea of molten rock. Beneath the crust lies the mantle, so hot that solid rock behaves like an incredibly slow-moving liquid. The continents rest on this mantle, drifting, colliding, and separating at rates of only a few centimeters per year. Over millions of years, these tiny movements reshape the world. Oceans open and close, mountain ranges rise, climates change completely. The continents we know are travelers, always in motion, even though the journey is invisible to us. This slow drifting once united all land into the supercontinent Pangaea and will one day bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers on its drifting plates, carried silently across geological seas. Earth's surface is constantly recycling itself through plate tectonics. Nothing on the planet's surface is permanent. Where plates collide, mountains rise. Where they separate, new ocean crust forms as molten rock wells upward. In other places, one plate sinks beneath another and melts back into the mantle, becoming part of the Earth once more. Even the ocean floor is born, spreads, and disappears on timescales of tens of millions of years. Every grain of sand, every cliff, every volcanic plain is part of this great planetary cycle. Earth is the only world we know that renews itself so completely, using heat and gravity to keep its surface alive. High above the clouds, the Himalayas continue to rise even now. Their growth began around 50 million years ago when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision has never stopped. Each year, the peaks climb a little higher, even as wind and glaciers carve them down. Every tremor, every deep earthquake is a whisper of immense pressure still at work. These mountains are not relics of the past, but living proof of Earth's patience and power. Continents drift as fast as your hair grows, and yet over geological time, that gentle pace reshapes the entire face of the planet. Continents slide on top of the mantle, carried by convection currents deep within Earth, while we rest quietly above, unaware of the vast, ancient journey beneath us. The Atlantic Ocean grows a little wider each year, while the vast Pacific slowly shrinks, almost imperceptibly, beneath the passage of time. This quiet movement happens at a pace so gentle that no human lifetime could ever notice it, yet it never stops. Over millions of years, the familiar maps we recognize today will become completely unrecognizable. Coastlines will shift, seas will open and close, and the shapes of continents will slowly transform. Africa will continue its gradual journey northward, pressing closer toward Europe. Australia will drift steadily upward, edging toward Asia. Far into the future, the continents may once again merge into a single giant landmass, repeating a pattern that has already occurred before in Earth's deep past. This slow continental drift explains some of the planet's greatest mysteries. Fossils of ancient creatures are found on continents now separated by vast oceans, revealing that these lands were once joined together. Entire mountain ranges on different continents share the same origins, their rocks matching perfectly like pieces of an ancient puzzle torn apart by time. The ground beneath your feet feels solid and permanent, yet it is part of a grand, restless voyage that began when the planet first formed and has never paused since. Earth is not a static world, but a traveler, endlessly reshaping itself through motion too slow for the eye to see. The ocean floor, hidden beneath miles of water, is younger than most of the continents above it. Beneath the waves lies a secret world in constant renewal. While the continents preserve rocks billions of years old, the seafloor is surprisingly youthful by comparison. Along vast mid-ocean ridges that wind around the planet like seams, molten rock rises from deep within the mantle. As it reaches the surface, it cools and hardens, forming brand new oceanic crust. This fresh crust slowly spreads outward in both directions, like a conveyor belt made of stone. As the seafloor drifts away from these ridges, it ages, cools, and becomes heavier. Eventually, at deep ocean trenches, it sinks back into the mantle where one tectonic plate slides beneath another. There, the old crust melts and is recycled once more into molten rock. Because of this continuous process, no section of ocean crust survives longer than about 200 million years, a fleeting moment in Earth's immense history. The continents, by contrast, are ancient survivors, floating above this cycle of destruction and renewal. If you could watch the planet's surface over deep time, you would see oceans forming and vanishing in a slow rhythm, like the steady rise and fall of a breath. The seafloor is the planet's heartbeat, endlessly renewing itself, reminding us that even the deepest and darkest places on Earth are alive with motion and change. Across the vast plains of the ocean floor, the rocks are marked with extraordinary patterns that resemble a barcode. These alternating magnetic stripes record moments when Earth's magnetic field flipped, with north and south swapping places. As new crust forms at mid-ocean ridges, minerals within the molten lava align themselves with the planet's magnetic field, acting like tiny compass needles. When the rock cools and solidifies, that magnetic direction becomes locked in place. Millions of years later, another reversal occurs, and the next band of rock records the opposite orientation. By studying these magnetic stripes, scientists can trace the history of Earth's magnetic reversals stretching back tens of millions of years. This discovery was one of the most important pieces of evidence supporting the theory of plate tectonics, revealing how the seafloor spreads outward over time. Beneath the oceans lies not chaos, but an orderly and elegant record of invisible forces, written patiently in stone by magnetism, heat, and the slow pulse of geological time. Rocks themselves can become natural magnets after cooling from lava. When molten rock erupts and begins to cool, tiny particles of iron and nickel inside the lava align with Earth's magnetic field. Once the rock hardens, those magnetic directions are frozen forever, preserving a snapshot of the planet's magnetic orientation at that precise moment. Scientists study these magnetic signatures to map the wandering paths of Earth's magnetic poles across deep time. Every reversal, every subtle shift is captured in stone as the planet's molten skin solidifies. These magnetic fingerprints helped prove that continents drift and seafloors spread. In every volcanic rock lies a silent record of Earth's magnetic pulse, whispering clues about ancient directions and unseen forces shaping the space around our world. The planet's memory is magnetic, written quietly into its iron-rich heart. Every volcano on Earth is connected to a hidden magma chamber far below the surface. Each volcano has a deep, fiery heart, a vast underground reservoir of molten rock. These magma chambers feed eruptions powerful enough to reshape landscapes and alter climates. Some chambers are small and shallow, others immense and deep, extending far beneath the crust. Inside them, crystals grow, gases rise, and pressure slowly builds. When the rock above can no longer contain that pressure, the magma finds a path upward, releasing lava and ash with staggering force. Between eruptions, these chambers remain hidden, slowly refilling and evolving over time. Using seismic waves, scientists can now glimpse their shapes, much like doctors use ultrasound to see inside the human body. Each volcano is part of a vast, interconnected system beneath the surface, a reminder that beneath quiet valleys and sleeping mountains lie glowing worlds of molten stone waiting patiently below. Some volcanic eruptions do not end quickly. Instead, they persist for hundreds of thousands of years. These eruptions, often linked to mantle plumes, release massive amounts of magma in events known as flood basalts. Lava spreads relentlessly, covering entire regions under miles of solid rock. The Deccan Traps of India and the Siberian Traps of Russia are remnants of such ancient firestorms. During these long eruptions, enormous amounts of gas and heat were released, changing Earth's climate and reshaping life itself. Standing on these hardened lava plains today, it is difficult to imagine the rivers of molten rock that once stretched endlessly toward the horizon. These landscapes remind us that Earth sometimes reshapes itself not through sudden violence, but through slow, unstoppable persistence. Basalt covers most of the ocean floor in dark, dense layers. If you could walk across the bottom of the sea, nearly every step would land on basalt, a heavy rock born from fire. It forms when molten material erupts along mid-ocean ridges and cools rapidly upon contact with seawater. The result is a vast, continuous crust that blankets the ocean basins like armor. Rich in iron and magnesium, basalt is darker and denser than continental rocks. Its layers are constantly renewed as new crust forms and old crust sinks back into the mantle. Beneath the waves, basalt holds the history of Earth's slowest and most patient movements, layer upon layer of cooled magma forming the quiet foundation of the oceans. When lava erupts beneath the sea, it cools so rapidly that it forms strange rounded shapes known as pillow lava. The outer surface hardens instantly while molten rock continues to push from within, creating bulbous, pillow-like forms stacked upon each other. These formations can blanket entire stretches of the seafloor. Each pillow is a frozen moment of motion, showing how fire and water meet in the depths. When geologists discover pillow lava on land, it reveals that the area was once submerged beneath an ancient ocean. These shapes are eerie and beautiful, like stone remembering its time as liquid. They are geological sculptures of time itself, proof that even in the darkest depths, Earth's creative forces never rest. In moments of explosive eruption, lava can cool so quickly that crystals never have time to form. The result is obsidian, volcanic glass, dark and gleaming, born in an instant. Smooth, sharp, and reflective, obsidian captures the raw speed of cooling fire, preserving a moment where molten chaos became frozen beauty in the blink of geological time. It is smooth, razor-sharp, and faintly reflective, a dark mirror born in an instant when molten rock collides with cold air or icy water and solidifies almost faster than the eye can follow. This material is obsidian, a volcanic glass that freezes fire in motion, capturing the energy of an eruption at the very moment it stops. For thousands of years, humans have recognized its perfection. Ancient civilizations shaped it into blades sharper than steel, into tools, arrowheads, and ceremonial ornaments that gleamed like frozen night. Even today, its edges are so precise that modern surgeons have experimented with obsidian scalpels. Yet beneath its glossy, mirror-like surface lies a story of violent transformation and sudden stillness. Obsidian is molten chaos halted mid-movement, heat turned fragile, energy transformed into something that can shatter with a single blow. When it breaks, it does not fracture randomly. Instead, it reveals elegant curved patterns known as conchoidal fractures, smooth ripples that seem to remember the way lava once flowed. Each break traces the ancient motion of fire, as if the stone itself recalls its liquid past. This dark, glassy rock stands as one of geology's greatest contrasts. Born in violence yet perfectly still, fragile yet timeless, a piece of Earth's inner fire captured forever in silence. Some rocks go even further, preserving pieces of Earth's ancient atmosphere itself. Locked inside microscopic hollows within certain stones, scientists have discovered tiny bubbles of air that have survived unchanged for millions, sometimes billions, of years. These minute pockets are true time capsules, sealing within them the chemical signature of skies long vanished. By studying their contents, Researchers can determine how much oxygen once filled the air, how much carbon dioxide warmed the planet, and how volcanic eruptions or the rise of life reshaped the balance of gases. Some of these bubbles formed as lava cooled and hardened. Others became trapped within sediments or ancient ice. Each one contains a ghost of an ancient breath, air once inhaled by early forests, drifting over reptile-ruled landscapes, or surrounding the first organisms to breathe. To hold such a rock is to hold a fragment of a vanished sky, a delicate and astonishing record of the ever-changing atmosphere that has linked all life across Earth's deep and unbroken history. There are mountains hidden beneath the sea that rise higher than Everest itself. Far below the rolling surface of the oceans lie immense mountain chains that dwarf the world's most famous peaks. Along the vast mid-ocean ridges, enormous volcanic ranges stretch for tens of thousands of miles, forming the longest mountain system on Earth, measured from their deep bases on the ocean floor to their summits. These submerged mountains rise even higher than Everest does above sea level. They exist in complete darkness, buried beneath crushing pressure, unseen by human eyes. Yet they are among the most active regions on the planet. Lava continually oozes from long cracks called fissures, building new peaks and valleys inch by inch over countless centuries. Some of these hidden giants, such as Mauna Kea, surpass the Himalayas when measured from base to summit. These underwater ranges remind us that much of Earth's true scale and beauty lies beyond sight. Vast silent kingdoms of stone that grow and shift beneath the waves, shaping the surface world without ever seeing the sun. Earth's deepest point lies nearly as far below sea level as airplanes fly above it. In the heart of the Pacific Ocean yawns the Mariana Trench, a colossal scar in the planet's crust so deep that if Mount Everest were dropped into it, its peak would still disappear beneath more than a mile of water. The trench's deepest known point, the Challenger Deep, plunges nearly 7 miles down, a distance comparable to the cruising altitude of passenger jets. Down there, the pressure is almost unimaginable, strong enough to crush steel and distort metal. Yet even in that extreme darkness, life persists. Strange, ghostly organisms glow faintly in the black water, feeding on chemical energy and thriving among mineral-rich sediments. The trench marks a powerful subduction zone where one tectonic plate slides beneath another and sinks back into the mantle. It is not merely the lowest point on Earth, but one of the planet's great engines of renewal, recycling crust back into the deep interior and reminding us how small the visible world truly is compared to the immense realm hidden below. The planet itself hums with countless micro-earthquakes you never feel. Even when the ground seems perfectly still, it is vibrating with the quiet murmurs of constant motion. Every day, thousands of tiny quakes ripple through the crust, releasing small bursts of energy as the Earth subtly adjusts to stresses deep underground. These movements are far too faint for human senses, yet sensitive instruments record them faithfully, capturing the whispers of shifting faults and migrating magma. Together they form a continuous background hum, the soft pulse of a living planet. This ceaseless trembling reveals where faults are slowly creeping, where pressure is building, and where volcanic systems are awakening. The stillness we perceive is an illusion. Beneath every mountain, forest, and ocean, the Earth sighs, cracks, and settles in secret rhythms that never truly stop. Sometimes, earthquakes are powerful enough to make entire rivers flow backward. When the ground shakes with overwhelming force, the landscape itself can tilt and deform in moments. During rare and violent earthquakes, sections of land may rise or sink so suddenly that rivers reverse their direction, flowing upstream against gravity. This phenomenon has been documented during events such as the Great New Madrid earthquakes of the early 19th century, when parts of the Mississippi River briefly ran backward. Fault movement can lift one side of the land or drop another, forming natural dams or altering valleys in seconds. For a fleeting moment, Earth's internal power overwhelms the steady pull that guides water downhill. When balance returns, rivers carve new paths through the altered terrain, bearing witness to the immense strength hidden beneath the crust. Not all tectonic motion arrives with destruction. Some faults move so slowly that no shaking occurs at all. Along certain fault lines, the crust slides in a process known as fault creep, where motion is steady, smooth, and silent. This gradual movement relieves pressure millimeter by millimeter, invisible to human senses but measurable by precise instruments. Faults in places like California and Turkey exhibit this behavior, gliding quietly while nearby segments remain locked and dangerous. These creeping sections may reduce the likelihood of large earthquakes locally, even as they transfer stress elsewhere. It is a subtle, constant balancing act, proof that even without drama, the ground beneath us is always in motion. At the very center of the planet lies a realm hotter than the surface of the sun. Earth's core is a sphere of solid and molten metal subjected to pressures beyond comprehension, with temperatures exceeding 9,000 degrees Fahrenheit. This immense heat is leftover energy from the planet's violent formation, combined with the slow decay of radioactive elements deep inside. Though forever beyond reach, the core drives volcanic eruptions, fuels plate tectonics, and generates the magnetic field that shields life from cosmic radiation. The liquid outer core flows like a vast metallic ocean, while the solid inner core rotates slightly faster than the surface above. This hidden furnace is Earth's beating heart, powering the movements, warmth, and resilience that make the planet alive. And deep within the mantle itself, scientists believe there may be an entire ocean hidden far below the surface, locked within minerals, silently cycling water through the deep interior of the world. Far beneath the Earth's crust, in a realm where rock glows under unimaginable heat and crushing pressure, scientists have uncovered minerals that hold astonishing quantities of trapped water. Locked deep within crystal structures, this water does not flow or pool as oceans do on the surface. Instead, it is bound atom by atom inside minerals formed under extreme conditions. These discoveries suggest that an entire ocean's worth of water, and perhaps even more, may exist hundreds of miles beneath our feet, hidden within the mantle itself. If this water were somehow released, it could fill the world's oceans many times over. This hidden reservoir is not a sea in any familiar sense, but a vast, silent archive of the same substance that sustains every living thing on the surface. Scientists believe tectonic plates may slowly drag water downward into this deep interior as oceanic crust sinks at subduction zones, only for it to return to the surface through volcanic eruptions and rising plumes of molten rock. This unseen circulation could be one of the fundamental reasons Earth has oceans at all. Even within the deepest stone, water endures, patiently waiting inside the mantle for millions of years, quietly shaping the planet from within. Crystals can grow larger than a human being in the hidden darkness of underground caves. Beneath the deserts of northern Mexico lies a subterranean cathedral unlike anything on the surface. The Cave of the Crystals, buried deep within a silver mine, contains translucent blades of gypsum that stretch more than 30 feet in length. Each crystal took hundreds of thousands of years to grow, forming in complete stillness within mineral-rich water heated by magma below. When the underground water eventually drained away, the crystals were left behind, frozen in time, gleaming like solid moonlight in the thick, humid air. To step into this cave is to enter another world, one not shaped by fire or force, but by patience, balance, and time beyond human comprehension. The precise conditions required to form such massive crystals are extraordinarily rare, demanding a perfect harmony of temperature, saturation, and stability. These towering formations remind us that even the hardest materials on Earth are capable of slow, graceful change when given enough time. They stand as monuments to stillness itself, sculpted by the quiet persistence of geological processes. Giant gypsum crystals shimmer within Mexico's Cave of the Crystals, deep below the surface where heat and humidity can overwhelm both machines and people in minutes. Discovered by miners in the year 2000, this hidden chamber contains crystal formations so immense they resemble pillars of light carved from glass. Some weigh dozens of tons and span the cavern like colossal beams, glowing softly in the darkness. They formed when mineral-rich groundwater remained at a stable temperature for hundreds of thousands of years, allowing gypsum molecules to arrange themselves into flawless symmetry. When the cave was drained, crystal growth ceased, preserving the scene forever. The environment remains so extreme that explorers can only enter for short periods. Yet even those brief visits reveal a vision of geological artistry created not by hands, but by water, chemistry, and the slow passage of time deep within the Earth. Salt domes can rise through solid rock like explosions unfolding in extreme slow motion. In regions where thick layers of ancient salt lie buried beneath heavier rock, pressure slowly forces the salt upward. Though solid, salt behaves like a viscous fluid under immense stress, flowing and deforming over millions of years. As it rises, it bends and fractures the rock above, forming towering dome-shaped structures that can reach miles in height. These salt domes often trap oil and gas, creating reservoirs that have shaped entire industries and civilizations. From the surface, they appear as gentle hills or subtle changes in the landscape, but beneath the ground, they are massive columns of silent motion. Each one tells the story of long-vanished seas that evaporated ages ago, leaving behind minerals that continue to migrate upward. They are proof that even solid ground can flow like a slow, unstoppable tide. Petrified wood is not simply wood turned to stone, but a transformation far more intricate and precise. When a tree is buried beneath volcanic ash or sediment, groundwater rich in dissolved minerals slowly seeps into its cells. Over thousands to millions of years, each microscopic structure of the wood is replaced molecule by molecule with quartz. This process preserves every growth ring, knot, and fiber in astonishing detail. The result is a fossil that looks like wood but feels cold, heavy, and crystalline to the touch. Trace elements can color the stone in vivid reds, yellows, and greens, painting natural patterns within the grain. Holding a piece of petrified wood is like holding a memory made solid, a living organism transformed into crystal by time itself. It is nature's reminder that nothing truly disappears, only changes form, carrying its story forward in stone. Coal began as ancient forests growing in swampy, prehistoric worlds. Long before humans existed, vast tropical forests thrived across the land. When these forests died, their remains sank into oxygen-poor swamps where decay slowed almost to nothing. Layer upon layer of plant matter accumulated, compressing under its own weight. Over millions of years, heat and pressure transformed this buried organic material into coal, a dense rock rich in carbon. Within every piece lies sunlight captured by ancient plants beneath a vanished sky. When coal is burned, that stored sunlight is released once more, energy returning from deep time. Each lump carries the imprint of long-lost forests, the breath of an ancient world condensed into dark, glittering seams beneath our own. Oil comes from the buried remains of ancient plankton that once drifted through primordial oceans. Long before dinosaurs walked the land, microscopic life flourished in the seas. When these organisms died, they settled onto the ocean floor and mixed with fine sediments. Over millions of years, heat and pressure transformed their carbon-rich remains into liquid hydrocarbons. Trapped within porous rock, these molecules became the oil that fuels modern civilization. Every drop once floated in sunlit waters, gathering energy through the simplest forms of life. In this way, the energy that powers our world is sunlight from Earth's distant past, stored beneath miles of stone. Oil tells a story not only of geology, but of biology, chemistry, and time intertwined in darkness. Every grain of sand carries the story of a vanished mountain. Each tiny particle was once part of something vast and solid, a towering peak or an ancient rock plateau. Over millions of years, wind, water, and ice wore those giants down, grinding them into ever smaller fragments. Rivers carried them toward the sea, waves reshaped them, and deserts scattered them across the land. What seems insignificant beneath our feet is the final chapter of a long geological journey, proof that even mountains eventually return to dust, continuing the endless cycle of transformation that shapes the earth. A single grain of sand may have lived a journey longer than any human lifetime. Before coming to rest beneath your feet, it might have been locked inside a towering mountain, crushed by the slow grind of glaciers, swept through deep canyons by ancient rivers, or carried across entire oceans by shifting currents. Some grains have traveled for millions of years, shaped and reshaped by wind, water, and ice. When viewed under a microscope, their edges, textures, and mineral makeup reveal clues about where they came from and the path they followed. Some still sparkle with quartz fragments born in ancient continental crust, remnants of landscapes long erased. Others are sharp volcanic shards, forged in fiery eruptions and shattered by sudden cooling. Every handful of sand is a silent library of time, a collection of broken worlds reduced to glittering fragments. And one day, these grains will be pressed together again, hardened into stone, lifted into mountains, and slowly broken apart once more, continuing the endless geological cycle. In a few rare deserts, sand itself can sing. When vast dunes shift and collapse, they produce a deep, resonant hum that can roll across the landscape for minutes at a time. These singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula, emit tones so pure and powerful they sound like the voice of the earth itself. The sound arises when countless grains slide past one another in perfect synchrony, vibrating together at a precise frequency, somewhere between the low note of a cello and the distant rumble of thunder. For this phenomenon to occur, the grains must be almost identical in size and completely dry, allowing friction to amplify their motion into sound. Travelers describe the experience as haunting and otherworldly, as if the dunes are breathing or speaking. Ancient cultures often believed these sounds were the voices of spirits or desert gods. In reality, it is physics and motion at work, transforming the landscape into a natural instrument that plays the slow, patient music of a shifting planet. Some beaches are not made from stone at all, but from life itself. Along certain coastlines, the sand beneath your feet is composed almost entirely of broken shells. Over centuries, the remains of tiny marine creatures such as mollusks, foraminifera, and coral have been ground down by waves into grains so fine they resemble powdered ivory. These biological sands can shine brilliant white beneath tropical sun, glow soft pink from crushed coral, or shimmer gold from microscopic algae. Each grain is a fragment of something that once lived, a small piece of ocean life returned to shore. Walking along such beaches feels like wandering through the ruins of invisible kingdoms, where waves have transformed the architecture of life into a shifting, living tapestry. Famous white beaches in places like the Bahamas and the Maldives stand as proof that beauty can be built not only by fire and stone, but by time, water, and biology working together. Earth's beaches come in colors far beyond white and gold. Some shores are black, green, pink, or even deep red. Black sands often line volcanic islands, formed when molten lava meets the ocean and shatters into fine glassy fragments. Green beaches appear where rare minerals like olivine rise from deep within the mantle and wash ashore. Pink sands are created from crushed coral and shell fragments mixed with pale quartz, while red sands are stained by iron-rich volcanic rock oxidized over time. Each color is a geological signature, a clue to the forces that shaped that place. Walking along these shores is like stepping across the planet's own palette, where every wave rearranges grains carrying memories of fire, water, and time. Glaciers carve landscapes like slow-moving rivers of stone. Though they may appear frozen and still, glaciers are always in motion. Over centuries, accumulated snow compresses into dense ice that flows downhill under its own weight. As these frozen rivers advance, they grind against mountains, polishing rock, carving valleys, and carrying debris for miles. When they retreat, they leave behind wide U-shaped valleys, scattered boulders, and clear lakes filling their abandoned paths. The marks of glaciers can be found across the globe, from the smooth granite domes of Yosemite to the dramatic fjords of Norway. Even today, glaciers continue their patient work, grinding ancient rock into fine dust that drifts across continents. They are sculptors of the earth, shaping land grain by grain through quiet persistence. Some glaciers move fast enough for their motion to be seen within hours. While most creep forward only inches per day, certain glaciers surge dramatically when meltwater lubricates the ground beneath them. In places like Greenland and Alaska, scientists have recorded glaciers racing forward at astonishing speeds, their fractured surfaces groaning and cracking as they move. Solid ice behaves like liquid stone, carrying enormous power as it reshapes valleys and transports massive boulders. To witness a glacier in motion is to see time itself accelerate, the slow rhythm of Earth briefly condensed into visible movement. Under immense pressure, ice behaves like slow-flowing honey. Beneath a glacier's surface, where pressure is intense and temperatures hover just below freezing, ice stops acting like a rigid solid. Instead, it bends and flows, its crystals deforming and sliding past one another. This allows entire glaciers to creep downhill over thousands of years, carving mountains as if they were soft clay. Laboratory experiments reveal how even solid materials blur the line between solid and liquid under enough time and weight. The planet's greatest transformations often happen not in sudden violence, but through quiet, relentless motion. Fossils can preserve moments as fleeting as raindrops. On slabs of ancient sedimentary rock, scientists have discovered delicate impressions left by rain that fell hundreds of millions of years ago. Each tiny crater marks a single drop striking soft mud during a storm that passed over a world long vanished. Almost instantly, the surface was buried by new sediment, sealing the marks in darkness until the rock hardened. When exposed again, these stones reveal weather from deep time, frozen forever. They remind us that even the briefest moments can survive for eternity. Some fossils preserve not just bones, but soft tissues, colors, and even feathers. For centuries, fossils were thought to capture only the hardest remains. Yet rare discoveries have revealed impressions of skin, muscle, and feathers, sometimes even preserving pigment that reveals the original colors of dinosaurs and ancient birds. These extraordinary fossils form when mineral-rich water replaces organic material before decay can erase it. In stone, the softness of life is preserved, allowing us to glimpse textures and colors from worlds that vanished millions of years ago. The result is not merely a fossil, but a moment of life turned into sculpture, preserved with astonishing precision. In some rare cases, these remains retain microscopic structures so fine that scientists can infer how ancient creatures moved, how they breathed, and even how their surfaces reflected sunlight in their distant world. To hold such a fossil is to bridge two vastly separated eras, to feel an echo of warmth, color, and motion from beings that vanished hundreds of millions of years ago. It is a quiet connection across deep time, a reminder that life leaves impressions far more lasting than flesh. Stromatolites record the oldest known evidence of life on Earth. Long before animals walked, swam, or crawled, and long before plants reached for the sky, simple microbial communities shaped the planet. These layered formations were built in shallow seas by mats of bacteria that trapped sediment and slowly stacked it upward, layer by layer, toward the sunlight. Known as stromatolites, they represent some of the earliest living structures ever formed. Some fossilized examples are more than 3.5 billion years old, placing them among the oldest direct records of life anywhere in the universe. Remarkably, stromatolites are not only relics of the past. They still grow today in a few isolated places, such as Shark Bay in Australia, where modern microbial mats continue their slow, rhythmic construction. Looking at one feels like gazing into the dawn of biology itself, a time when life was quiet, simple, and patient. They remind us that the foundation of all complexity began with thin living films, turning light, water, and time into the groundwork of the living world. Earth itself once became almost entirely frozen during an event known as Snowball Earth. Around 700 million years ago, the planet may have been locked in ice from pole to equator. Vast glaciers sealed the oceans beneath miles of frozen crust, reflecting sunlight back into space and plunging the world into a deep and prolonged chill. Volcanic activity, shifts in atmospheric gases, and changes in solar energy likely combined to trigger this global freeze. For millions of years, Earth existed as a silent, white sphere beneath a dim sun. Yet even then, life endured. Hidden beneath ice, near volcanic vents, and in pockets of liquid water, organisms survived in the shadows. Eventually, relentless volcanic eruptions released enormous amounts of carbon dioxide into the atmosphere. With the oceans sealed, the gas could not dissolve as it normally would, and heat slowly built up. When melting began, it accelerated rapidly. Dark rock absorbed sunlight, warming the surface further, and the planet thawed in a dramatic, world-spanning release. The return of liquid oceans may have helped spark an explosion of complex life. Snowball Earth stands as one of the greatest transformations in planetary history, a near extinction followed by renewal, Written in ice and fire, volcanoes may have been the quiet force that ended this frozen age. Even beneath miles of ice, they continued to erupt, steadily releasing greenhouse gases over millions of years. When the thaw finally began, the transformation was swift. Floods surged across newly exposed land, erosion reshaped continents, and chemical changes in the oceans may have nourished early life. In this way, volcanoes acted as guardians of planetary balance, their persistent heat preventing Earth from becoming permanently frozen. What began as an age of silence ended as one of rebirth, proving that even in the deepest cold, renewal waits patiently beneath the surface. The oxygen in our atmosphere was first created by ancient microbial mats. The air we breathe today owes its existence to microscopic organisms that lived billions of years ago. These early microbes, ancestors of modern cyanobacteria, thrived in shallow seas and used sunlight to split water molecules, releasing oxygen as waste. At first, this oxygen reacted with dissolved iron in the oceans, forming vast deposits of rust-colored minerals. Only after the oceans became saturated did oxygen begin to accumulate in the atmosphere. This transformation, known as the Great Oxidation Event, changed the planet forever. It allowed complex cells to evolve and eventually made possible plants, animals, and ecosystems as we know them. Every breath you take is a gift from those ancient microbes, whose simple chemistry reshaped the world and paved the way for life on land and sea. Banded iron formations mark the moment the planet began to breathe. Found in ancient seabeds around the world, these striped layers of red and gray rock are the fossilized record of rising oxygen. As early microbes released oxygen, it reacted with iron in seawater, forming rust-like particles that settled to the ocean floor. Over millions of years, these sediments hardened into stone, preserving the chemical history of a transforming planet. Today, these formations are mined for iron, the backbone of modern civilization. Yet they began as a byproduct of microbial life. Each band is a pulse in Earth's awakening, a visible heartbeat marking the slow transition from an airless world to one rich in oxygen. There was even a time when Earth's oceans may have appeared purple. Before oxygen dominated the atmosphere, the seas were inhabited by microbes that used sulfur compounds rather than oxygen to harness sunlight. These organisms produced pigments that may have tinted the water in shades of red, violet, and purple beneath an orange-tinged sky. As oxygen-producing bacteria spread, these colors slowly faded, replaced by the blue oceans we recognize today. This shift from a sulfur-based world to an oxygen-rich one was among the most profound transitions in Earth's history. For a time, our planet glowed in colors almost impossible to imagine, seas of violet under a dim sun, as life experimented with light long before forests, reefs, or animals existed. Entire mountain ranges have risen and vanished without a trace. The continents we see today are only a temporary expression of Earth's surface. Over deep time, massive mountain chains have been worn down so completely that nothing remains but flat plains. Wind, water, ice, and gravity patiently erase even the tallest peaks, grain by grain. Sometimes, the deep crystalline roots of ancient mountains survive, buried beneath younger layers of rock, waiting to be discovered. Over hundreds of millions of years, erosion can erase a mountain as thoroughly as waves smooth a pebble. The planet is always rebuilding itself, and what seems eternal to us is merely a fleeting sculpture in geology's ongoing work. Continents have collided and split apart many times throughout Earth's history. Driven by heat rising from the mantle, the crust has folded, fractured, and rearranged itself again and again. Each collision raised new mountains. Each separation opened new oceans. This repeating pattern, known as the supercontinent cycle, has occurred multiple times over billions of years. When continents collide, rocks are buried deep, transformed by heat and pressure, and eventually returned to the surface reborn. Earth's surface is never finished. It is always becoming something new, shaped by forces so slow and powerful that they turn destruction into creation, again and again. When tectonic plates pull away from one another, fresh crust is born in the widening gap, slowly cooling as molten rock rises from deep within the Earth. Embedded within this newly formed surface are fragments of unimaginably ancient worlds, pieces of continents that once existed long before modern geography took shape. The scars of these immense migrations are still visible today, written quietly into the planet itself, revealed through matching fossils, mirrored rock formations, and identical mineral layers discovered on opposite sides of vast oceans. These clues tell a powerful story. The land beneath our feet is not permanent or fixed, but part of a restless, ongoing dance that has never truly stopped. The ground we stand upon has traveled across the globe over hundreds of millions of years, carrying within it the buried history of countless vanished worlds, each layer a memory of ancient mountains, seas, and skies. Long before the continents we recognize today existed, Earth assembled and broke apart again and again. There have been at least 6 supercontinents before our own era. Before Pangaea, before even Rodinia, the planet repeatedly gathered its land into colossal unified masses, only to tear them apart once more. Each of these supercontinents possessed its own towering mountain ranges, sweeping oceans, and unique climates, all rising and falling in cycles recorded silently in stone. Names like Nuna, Columbia, Rodinia, Pangaea, and Gondwana are given to these lost worlds, their remnants now scattered across the modern globe like fragments of a shattered mosaic. When these ancient continents existed, life on Earth was often small and microscopic, yet their formation profoundly shaped ocean chemistry, atmospheric composition, and planetary circulation. Every collision and separation altered climate patterns, redirected deep ocean currents, and steered the slow course of evolution itself. The continents we inhabit today are survivors, broken pieces of those ancient giants, living proof that Earth's surface is temporary, forever changing, and never whole for long. To study them is to read Earth's autobiography, written across deep time in drifting stone. Pangaea was merely the most recent chapter in this endless cycle. Around 250 million years ago, nearly all of Earth's land merged into one immense supercontinent surrounded by a single global ocean. This colossal landmass stretched from pole to pole, connecting regions now separated by entire hemispheres. Its vast interior was harsh and arid, isolated from the moderating influence of the sea, while its coastal edges teemed with early forests, amphibians, and reptiles adapting to a changing world. Over tens of millions of years, heat rising from deep beneath the crust built enormous pressure. Eventually, cracks formed, and the continent began to split apart. The Atlantic Ocean slowly opened, and the continents drifted toward the positions we recognize today. Fossils of identical plants and animals found on opposite shores serve as silent witnesses to that ancient unity. The breakup of Pangaea reshaped global climate, ocean circulation, and life itself, setting the stage for everything that followed. It was not the first supercontinent, and it will not be the last, only one moment in Earth's unending drift. Even now, the next supercontinent may already be forming beneath the Pacific Ocean. Far below the waves, tectonic plates continue their slow, relentless movement, preparing the next great rearrangement of Earth's surface. Scientists predict that in 200 to 300 million years, the continents may once again converge into a new supercontinent. Some models suggest the Pacific Ocean will close as Asia and the Americas drift together, forming a vast landmass sometimes called Amasia. Other models envision the Atlantic closing instead, drawing Europe and the Americas back together. Though the exact outcome remains uncertain, the process itself is inevitable. The same unseen forces that tore Pangaea apart are still at work today, shifting continents inch by inch. To imagine Earth that far into the future is to realize how temporary our maps truly are. The planet is always rebuilding itself, and deep below, the first subtle motions of the next supercontinent have already begun. Australia is one of the clearest examples of this quiet movement. Beneath the continent, the tectonic plate carrying Australia is slowly gliding northward at a pace of just a few centimeters per year. Over millions of years, this gentle drift accumulates into journeys spanning thousands of kilometers. Eventually, Australia will collide with Southeast Asia, lifting new mountain ranges and reshaping coastlines. Satellite measurements already track this motion with astonishing precision. Powered by slow convection currents in the mantle, heat from Earth's core moves vast slabs of rock, as if they were rafts floating on a molten sea. Though imperceptible in daily life, this movement transforms maps, alters climates, and reshapes ecosystems. Coral reefs grow where land once stood, deserts drift toward the tropics, and one day entirely new mountain chains will rise between continents. Australia's slow northern voyage is among the most graceful migrations on Earth. Africa, too, is in motion, and may one day split apart entirely. Deep within East Africa, a massive rift stretches for thousands of kilometers, marking the place where the continent is slowly tearing itself in two. Volcanic eruptions, earthquakes, and thinning crust reveal that a new ocean may someday be born here. The East African Rift is a powerful reminder that continents are not rigid, but flexible, bending and stretching like skin over a living planet. In tens of millions of years, regions including Ethiopia, Kenya, and Tanzania may separate from the rest of Africa, drifting eastward as an entirely new landmass. Lakes such as Tanganyika and Malawi fill the deep scars of this rift, early hints of the ocean that will eventually flood in. Standing at its edge is like witnessing the birth of a future continent. The process is unimaginably slow, yet it is unfolding right now beneath our feet. Iceland offers another rare glimpse into Earth's inner workings. The island exists because it sits directly atop the mid-Atlantic ridge, where two tectonic plates are pulling apart. Here, molten rock rises through a long tear in the crust, cooling to form new land. Iceland is a dramatic crossroads of fire and ice, where glaciers rest beside active volcanoes. Hot springs, geysers, and lava fields testify to the restless energy below. Periodic eruptions remind residents that their homeland is still under construction. Because this plate boundary rises above sea level, Iceland allows scientists to observe the mechanics of plate tectonics in plain view. It is a living laboratory of creation, where the Earth visibly grows at the boundary between the frozen North Atlantic and the molten depths below. Far out in the Pacific, the Hawaiian Islands tell a different but equally revealing story. They were formed by a stationary hotspot deep within the mantle, a plume of molten rock that punches through the moving crust. As the Pacific plate drifts northwest, each eruption creates a new island that slowly moves away, allowing another to form in its place. This has produced a long chain of islands and submerged mountains stretching thousands of kilometers across the ocean floor. The youngest island, Hawaii, still glows with flowing lava, while older islands have eroded into low atolls. By tracing this chain, scientists can map the motion of the Pacific plate over millions of years. The hotspot remains fixed while the surface glides above it, leaving behind a dotted trail of time and motion. Yellowstone hides one of the largest volcanic systems on Earth. Beneath its forests and geysers lies an immense reservoir of magma capable of fueling one of the most powerful eruptions ever known. Steaming vents, bubbling pools, and erupting geysers are surface expressions of the intense heat below. Scientists closely monitor the region, mapping vast magma chambers stretching dozens of kilometers beneath the crust. While an eruption is not expected anytime soon, past explosions reshaped much of North America, scattering ash across entire continents. Today, Yellowstone releases pressure through its geysers, offering a constant reminder of its inner fire. Supervolcanoes like this have the power to alter global climate for centuries. When they erupt, sunlight can be blocked, temperatures can plunge, and ecosystems can struggle to survive. Though rare, these events reveal the delicate balance between Earth's deep interior and the fragile surface world we inhabit. The immense power locked beneath our feet has shaped the course of life itself, driving evolution forward while occasionally sweeping it back in waves of destruction. Across deep time, this hidden energy has triggered mass extinctions that erased dominant species, only to open space for new forms of life to rise and flourish. Yet even in their most violent moments, supervolcanoes are not forces of chaos alone. They are part of the planet's long, steady rhythm of renewal, endlessly cycling material between the crust, the atmosphere, and the mantle. Through fire and ash, they reshape landscapes, alter climates, and remind us that life and flame have always been deeply entwined. The same eruptions that bring devastation also fertilize soils, reshape ecosystems, and reset the conditions for future life. The largest known volcanic eruption in Earth's recent history occurred in what is now Indonesia. Around 74,000 years ago, a colossal explosion at Lake Toba released unimaginable energy. More than 2,000 cubic kilometers of ash and magma were hurled into the sky, carving out a vast caldera nearly 100 kilometers wide, a scar still visible from space today. The eruption darkened skies across the globe, dimming sunlight and lowering global temperatures. Ash fell across continents, settling into oceans, forests, and ice sheets. Some scientists believe this event triggered a brief volcanic winter, placing immense stress on early human populations and possibly reducing their numbers dramatically. Long after the eruption ceased, volcanic gases lingered in the atmosphere, cooling the planet and tinting sunsets with eerie reds and purples for years. Compared to this event, every eruption in recorded history appears small. Today, the lake filling the caldera looks peaceful and serene, but beneath its still surface lies one of the most powerful geological wounds the planet has ever endured. It stands as a reminder that Earth's greatest acts of creation often arrive hand in hand with destruction. Some eruptions have left traces that still circle the planet today. Fine volcanic ash can drift in the upper atmosphere for years, carried by powerful winds that wrap endlessly around the globe. Particles from eruptions such as Mount Pinatubo or Krakatoa have been detected long after the explosions ended. These microscopic fragments scatter sunlight, subtly cooling global temperatures and producing vivid sunsets that once inspired painters and poets. High above weather systems, ash forms thin veils that alter how light moves through the sky. Some of these particles eventually settle back to Earth centuries later, preserved in ice cores and ocean sediments as silent records of ancient eruptions. Every major volcanic event, no matter how distant, becomes part of the shared atmosphere of the entire planet. The air we breathe today still carries echoes of eruptions from long ago, a reminder that even the calmest sky holds the memory of Earth's fiery breath. In a few rare places, lava lakes remain molten for decades without cooling. Within volcanic craters such as Erta Ale in Ethiopia and Kilauea in Hawaii, pools of molten rock persist in a delicate balance. Constant supplies of heat and magma rise from below, preventing the lava from solidifying. Their surfaces churn and ripple like fiery oceans, briefly crusting over before breaking apart again. At night, these lakes glow intensely, casting orange light against black rock and drifting smoke, like open windows into the planet's core. Their stability is so precise that they can endure for decades, continually refreshed by deep circulation. Watching a lava lake is hypnotic, a living furnace breathing slowly in rhythmic motion. For scientists, these lakes offer rare opportunities to study magma directly, revealing chemical and physical processes impossible to replicate in laboratories. Each one stands as proof that Earth's internal fire still burns fiercely beneath its thin, cooling shell. Lightning can even strike within volcanic ash clouds. As a volcano erupts, billions of ash particles collide violently, building immense electrical charges. When those charges discharge, lightning bolts crackle through towering plumes of ash and gas. These volcanic lightning storms can illuminate entire skies, creating scenes of fire and electricity above erupting mountains. Unlike ordinary thunderstorms, these flashes are born purely from rock, friction, and explosive force. Photographs capture branching bolts tearing through columns of black smoke, each strike lasting only moments but carrying immense power. Scientists study volcanic lightning to better understand ash movement and eruption intensity, since increased lightning often signals more violent eruptions. To witness such a storm is to see Earth's elements merge, solid, liquid, gas, and electricity, into a single, breathtaking display where destruction briefly shimmers with extraordinary beauty. When volcanoes meet ice, the results are especially explosive. In regions where glaciers rest atop volcanic systems, rising magma melts vast quantities of ice in moments. The sudden release of water produces expanding steam with tremendous force, blasting through ice and rock alike. These eruptions can trigger floods, ash clouds, and massive reshaping of the landscape. Iceland's volcanoes often erupt this way, hidden beneath thick ice caps until pressure becomes unbearable. The interaction between fire and ice creates unique landforms known as tuyas, flat-topped mountains formed when lava erupts beneath glaciers. Each eruption beneath ice rewrites the land, proving that even nature's most opposing elements are connected within the same cycle of creation and transformation that has shaped Earth since its earliest days. Entire new islands have even risen from volcanic eruptions within living memory. Across the world's oceans, submarine volcanoes occasionally erupt with enough force to build land from the seafloor upward. In the past century alone, eruptions near Iceland, Japan, and Tonga have created brand new islands that steamed and hardened under the sun. Some were quickly reclaimed by waves, while others stabilized and began to host life. Birds arrived first, followed by plants, insects, and eventually complex ecosystems. These newborn islands offer a glimpse into how continents formed long ago. Watching land rise from the sea is to witness planetary creation unfolding in real time. Earth is not finished shaping itself, continues to build, erode, and begin again one eruption at a time. Some lakes hide dangers just as powerful as volcanoes. In parts of Africa, deep lakes contain enormous amounts of dissolved carbon dioxide trapped beneath their surfaces. When pressure or temperature shifts suddenly, the gas can erupt upward in an invisible, suffocating cloud. In the 1980s, Lake Nyos in Cameroon released such a burst, silently killing people and animals in nearby valleys. Scientists now closely monitor these lakes, installing systems to release gas gradually before pressure becomes lethal. These limnic eruptions originate from volcanic sources beneath lake beds, where gas seeps upward and dissolves into water like carbonation in a sealed bottle. When released, the result is sudden and deadly, a rare reminder that even calm waters can conceal immense energy. Sinkholes offer yet another example of Earth's hidden motion. Beneath many cities and landscapes, underground cavities slowly form as limestone or salt dissolves in moving groundwater. When the roof of one of these voids collapses, the ground above can suddenly give way. Sinkholes can open in seconds, swallowing roads, cars, trees, and buildings without warning. Heavy rainfall often triggers collapses by weakening underground layers. Scientists now use radar and ground sensors to map vulnerable regions, seeking to detect hidden voids before disaster strikes. Though dramatic, sinkholes are part of Earth's quiet recycling of rock, shaped patiently by water working below the surface. Karst landscapes conceal entire rivers flowing silently through stone. In regions dominated by limestone or dolomite, rainwater slowly dissolves the bedrock, carving vast underground networks of tunnels, caverns, and channels. Rivers vanish beneath the surface, traveling unseen for kilometers before emerging again as springs. These hidden waterways shape the land from below, forming sinkholes, caves, and natural bridges. They remind us that much of Earth's activity happens out of sight, beneath our footsteps, sculpting the planet in darkness. Beneath the surface of the Earth lies a vast and intricate hidden world, one that stretches far beyond what the eye can see or the mind can easily imagine. These underground systems can extend for hundreds of kilometers, carrying entire rivers silently beneath the land we walk on every day. Water flows through darkness, carving stone grain by grain, forming networks that rival surface river systems in scale and complexity. Above these concealed waterways, the land can weaken and collapse over time, giving rise to sinkholes, valleys, and sharp, broken ridges that define what is known as karst terrain. In these regions, a stream may suddenly vanish into a cave opening, only to reappear many miles away as a crystal-clear spring, as if the Earth itself is breathing water in and out. Entire ecosystems have evolved to survive within these lightless passages. Blind fish glide through black currents, insects grow translucent and fragile, and life adapts to a world without sunrise or sunset. Karst landscapes exist on every continent and provide drinking water for millions of people, yet their hidden nature also makes them especially vulnerable to pollution. To explore these underground networks is to enter the circulatory system of the planet itself, where stone and water move together in an endless dialogue of dissolution, shaping, and renewal, transforming the surface of the Earth drop by drop across unimaginable spans of time. Within these caves, Stone appears to grow like living tissue. Stalactites descend slowly from the ceiling, while stalagmites rise patiently from the floor, and over centuries or even millennia, they may meet to form towering pillars that seem to hold the cave aloft. Each formation begins with a single droplet of water. As it falls, it carries dissolved minerals from the limestone above. When the droplet evaporates, it leaves behind a microscopic ring of calcite. Over countless repetitions, these rings lengthen downward into delicate stalactites. Where the droplets land, matching mounds rise upward as stalagmites. Eventually, these twin structures connect, forming columns that resemble frozen waterfalls sculpted by time and patience. Growth is so slow that it is measured in millimeters per century. Lantern light reveals their fragile textures, each ridge and ripple preserving a record of ancient rainfall, climate shifts, and chemical changes in the water. Together, they resemble forests of stone, where every branch and column was born from darkness, shaped by gravity, and infused with the memory of rain falling through the earth over ages beyond human comprehension. Cave formations grow far more slowly than fingernails, making their beauty a testament to patience rather than force. Flowstones, crystal draperies, and mineral curtains accumulate layer by layer as thin films of water deposit traces of stone. A single centimeter of growth may take hundreds of years, depending on temperature, mineral content, and the steady rhythm of dripping water. Some formations still glisten with moisture from drops that began their journey through soil and rock decades ago. Scientists study these layers like pages in a book, reading stories of ancient droughts, floods, and climate patterns long before written history existed. Walking through a cavern feels like stepping inside a clock that moves at the speed of geology, where time advances not by seconds, but by crystallization. These subterranean sculptures remind us that beauty does not always emerge from speed or violence, but from stillness, repetition, and persistence beyond any human scale. Some caves even possess their own weather systems. Deep within large cave networks, microclimates develop that differ completely from the surface world. Temperature, humidity, and airflow interact to create drifting fogs, gentle winds, and subtle atmospheric movements. Warm air rising from deeper passages meets cooler air near entrances, forming slow, swirling currents that behave like miniature weather fronts. Certain caves seem to breathe, exhaling warm air during winter and inhaling cool air during summer. As conditions outside change, moisture condenses along stone walls, dripping steadily to nourish delicate formations and hidden ecosystems. Stepping inside such a cave feels like entering the lungs of the planet, where rock and air move together in quiet rhythm. These stable environments preserve fossils, ancient artifacts, and rare species that cannot survive elsewhere, reminding us that even the most solid parts of Earth are filled with motion, breath, and living atmosphere. Earth's longest known cave stretches for hundreds of miles beneath the rolling hills of Kentucky. Mammoth Cave, the largest cave system ever discovered, extends for more than 400 miles, with new passages still being found today. Ancient rivers carved this labyrinth over millions of years, dissolving limestone and branching endlessly through the bedrock. Explorers navigate narrow crawls, vast chambers, and underground rivers that continue to reshape the cave even now. The air remains cool and still, and the silence feels almost alive, pressing gently against the senses. Mammoth Cave challenges the imagination, revealing how much of our planet exists unseen beneath our feet. It stands as both a geological marvel and a living archive of time, carved patiently by water into a cathedral of stone that disappears into darkness without end. Earthquakes remind us that even time itself is not fixed. When massive earthquakes shift enormous amounts of rock, they subtly alter the planet's rotation. The change is tiny, measured in microseconds, but it is real. By redistributing Earth's mass, quakes slightly adjust its moment of inertia, much like a spinning skater changing speed by moving their arms. After the 2004 Sumatra earthquake, scientists calculated that the length of the day shortened by a fraction of a second. The quake also nudged the planet's poles and altered Earth's shape ever so slightly. These events reveal that even the rhythm of day and night is influenced by the deep movements of rock and gravity, and that every earthquake echoes through the mechanics of the entire planet. The energy released by major earthquakes does not stop at the epicenter. Seismic waves travel through the earth like sound through a bell, circling the globe multiple times before fading. Instruments detect these vibrations as they reflect and bend through the crust and mantle, allowing scientists to map the planet's interior. The largest earthquakes cause the entire Earth to tremble, flexing its surface as energy passes from one hemisphere to the other. These global reverberations transform the planet into a single, vibrating instrument, humming briefly with its own internal heartbeat. Some earthquakes release energy equivalent to millions of tons of TNT. The shaking felt at the surface is only a fraction of the total force involved. Most of the energy moves deep underground, shifting rock layers heavier than entire mountain ranges. During the 2011 Tohoku earthquake in Japan, the energy released was powerful enough to move the seafloor by meters and alter Earth's rotation. Such events remind us that the crust is under constant tension, storing and releasing energy in a slow but unstoppable rhythm that shapes continents and oceans over geologic time. Deep beneath the surface, rock itself can flow like putty. Though stone feels solid to us, extreme heat and pressure cause it to deform slowly, bending rather than breaking. Over millions of years, this movement allows mountains to rise, fold, and transform. Minerals stretch and twist, creating the patterns seen in metamorphic rocks exposed at the surface today. Laboratory experiments confirm that under enough heat and pressure, rock behaves like a viscous fluid. The mantle flows this way constantly, driving the movement of continents above. It is a powerful reminder that even the hardest materials are capable of motion, and that the strength of stone lies not only in its rigidity, but in its ability to yield, reshape, and endure through time. Metamorphic rocks serve as silent archives of pressure and heat deep within the planet, preserving a detailed record of the forces that operate far below the surface. When rocks are buried deep inside the Earth's crust, they do not simply remain unchanged. Instead, they are transformed by immense temperatures and crushing pressures that reorganize their internal minerals without melting them completely. This slow, powerful process alters their texture, structure, and strength, turning familiar materials into entirely new forms. Granite is transformed into gneiss, limestone becomes marble, and shale is reshaped into slate. Each metamorphic rock carries within it a memory of the conditions it endured, like pages written into a geological diary. By studying these mineral arrangements, scientists can reconstruct ancient mountain-building events, identify how deep rocks were once buried, and even determine the direction in which tectonic plates moved long ago. Some formations display aligned minerals that act like frozen arrows, pointing toward the forces that shaped them. When uplift and erosion eventually bring these rocks back to the surface, they offer a rare glimpse into the planet's internal history, preserved in crystalline form. These are stones that remember, holding within their folds the invisible energies that constantly flow beneath the crust, revealing that every mountain range was once hidden deep below, rewritten again and again by heat, pressure, and time. Slate tells one of the most subtle yet powerful stories of transformation. It began as soft mud settling quietly beneath ancient seas, where fine sediments drifted downward and formed delicate layers on the ocean floor. Over millions of years, additional layers piled on top, compressing the mud beneath immense weight. Water was slowly squeezed out, and clay minerals aligned themselves into flat, orderly sheets. With the added influence of heat and pressure, the mud hardened into slate, a rock so finely layered it can be split into smooth, durable tiles. This transformation is a story of stillness becoming strength, of patience hardened into permanence. Slate once formed entire seafloors, yet today it roofs homes, lines pathways, and carries the imprint of vanished oceans into the modern world. When held up to the light, slate reveals a soft sheen from its compressed minerals, tiny echoes of clay particles that once floated gently through seawater. It stands as proof that even the softest materials, given enough time and pressure, can become enduring and resilient. Marble began its journey long before it gleamed in temples, sculptures, and monuments. Its origins lie in limestone formed on ancient seafloors, composed of countless shells and skeletons from coral, plankton, and mollusks that lived and died in prehistoric oceans. Over millions of years, these remains compacted into thick layers of limestone. When buried deep within the earth, heat and pressure caused the calcite crystals to grow and interlock, erasing visible fossils and transforming the rock into marble's smooth, dense structure. Trace minerals introduced subtle colors, iron lending red tones, serpentine creating greens, graphite adding shades of gray. When polished, these minerals catch and scatter light, giving marble its famous glow, as if it holds sunlight within its surface. Ancient civilizations valued marble for this luminous quality, unaware that it was truly the memory of oceans made solid. Every polished column and carved statue was once part of a living sea, transformed by geological forces into timeless beauty. Every gemstone carries the story of its birth deep within the earth. Hidden beneath layers of rock, heat, pressure, and chemistry work together to create crystals of extraordinary beauty. Diamonds form under crushing forces hundreds of kilometers below the surface, while emeralds grow in mineral-rich veins where water and rock exchange rare elements. Rubies, sapphires, topaz, and quartz each emerge from precise conditions of temperature and chemistry that seldom align. Their rarity makes them precious. When cut and polished, their clarity reveals the harmony of their atomic structures, offering a glimpse into order forged within chaos. Gemstones travel from deep rock to human hands through volcanic eruptions, erosion, and immense spans of time. Each one is a messenger from a different environment inside the planet, carrying a record of hidden geological processes. To gaze into a gemstone is to look backward into Earth's memory, seeing patience, pressure, and crystallization frozen into perfect symmetry. Rubies and sapphires, though seemingly different, are born from the same mineral, corundum. In its pure form, corundum is colorless, composed of aluminum and oxygen arranged in a tightly packed lattice. When traces of chromium enter this structure, the crystal glows red and becomes a ruby. When iron and titanium take their place, the result is blue sapphire. Other trace elements create yellow, green, or pink variations. These tiny atomic substitutions alter how light moves through the crystal, producing dramatic changes in color. The fact that two of the world's most prized gemstones share the same foundation shows how subtle changes at the smallest scale can produce astonishing beauty. Every color is a fingerprint of chemistry, proof that nature's artistry begins with invisible interactions deep within the earth. Emeralds form only under some of the rarest geological conditions on the planet. They require the unlikely meeting of silica-rich rocks and beryllium-bearing fluids, environments that almost never intersect. When they do, the mineral beryl forms, colored green by traces of chromium or vanadium. This delicate balance occurs in only a few tectonically active regions where the Earth has blended these ingredients over millions of years. Most emeralds contain tiny fractures and inclusions known as gardens, internal features that record the stresses of their formation. These are not flaws, but signatures of authenticity, proof that the stone is a true product of geological struggle. To hold an emerald is to hold the story of improbable chemistry, immense pressure, and extraordinary patience made visible. Opal forms in a completely different way, born not from crystals but from ancient groundwater moving slowly through silica-rich rock. As water seeped through cracks and voids, it deposited microscopic spheres of silica that stacked in precise layers. These spheres scatter light, producing opal's signature rainbow shimmer known as play of color. Many opals formed in landscapes that were once wet but later turned arid. As the water vanished, it left behind these glowing structures. Under magnification, opal reveals an intricate order hidden within apparent chaos. Australia's famous opal fields were once part of an ancient inland sea where these processes quietly unfolded. Each opal captures not only light, but the memory of vanished rain, lost rivers, and the chemistry that transformed water and sand into fire frozen in stone. Meteorites found on Earth tell stories from before our planet even existed. These fragments of space rock formed billions of years ago from the same cloud of dust and gas that gave birth to the sun and planets. Some contain minerals unchanged since that time, preserving ancient chemistry from the dawn of the solar system. Scientists study meteorites to understand how planets formed, melted, and separated into cores and crusts. Some even contain organic compounds, suggesting that the ingredients for life were present long before Earth took shape. To hold a meteorite is to touch something older than our world itself, a traveler across time and space carrying the memory of creation in its structure. Some rocks, quite literally, are older than the solar system, reminding us that Earth is only one chapter in a much larger cosmic story. Within certain meteorites, scientists have discovered microscopic grains known as presolar dust, extraordinary remnants of ancient stars that existed long before our sun was ever born. These unimaginably tiny crystals formed in the outer layers of dying stars, created under extreme heat and pressure as those stars reached the final stages of their lives. As these ancient stars shed their outer material through powerful stellar winds, the grains were released into the vastness of space, beginning a journey that would last billions of years. Drifting slowly through the galaxy, surviving radiation, shockwaves, and cosmic collisions, these particles eventually became trapped within the swirling cloud of gas and dust that collapsed to form our solar system. Their isotopic fingerprints reveal unmistakably alien origins, chemical signatures that differ from anything naturally produced on Earth. To find such grains embedded within a meteorite is to uncover stardust untouched by planetary processes, matter that predates Earth itself. When scientists analyze these particles, they are not merely studying minerals, but reading stories written before the sun ever rose. They carry echoes of supernova explosions and the slow, steady breath of red giant stars. Each grain is a whisper from the galaxy's distant past, powerful proof that the Earth itself was formed from recycled stellar material, born from the remains of long-dead stars. Lunar rocks brought back by astronauts have also played a crucial role in helping scientists date Earth's earliest crust. The samples collected during the Apollo missions did far more than reveal the Moon's own history. They unlocked secrets about Earth's violent beginnings. The isotopic composition of lunar rocks closely matches that of Earth's mantle, strongly supporting the theory that the Moon formed from debris left behind after a colossal collision between the young Earth and another planet-sized body. By studying these rocks, scientists were able to estimate that Earth's crust first solidified around 4.5 billion years ago, offering one of the most important timestamps in our planet's history. Some of the oldest lunar basalts also preserve scars from impacts that shaped the early solar system. Their surfaces, pitted by countless micrometeorite strikes, have remained virtually unchanged for eons, preserving a record of ancient bombardment that has long been erased from Earth by erosion and plate tectonics. Every moon rock brought home is a time capsule, connecting two worlds forever linked by a single, violent origin story written in dust, fire, and unimaginable force. The oldest minerals ever found on Earth are tiny zircons discovered in ancient rocks of Western Australia. These microscopic crystals date back more than 4 billion years, forming soon after the Earth itself came into existence. Despite surviving endless cycles of erosion, burial, heating, and metamorphosis, these resilient minerals endured, preserving chemical clues from the planet's earliest era. Inside each zircon lies a trace of uranium that has slowly decayed into lead over immense spans of time, allowing scientists to measure their age with extraordinary precision. Even more remarkably, the composition of these zircons reveals that liquid water already existed on Earth when they formed, suggesting that the planet's surface cooled far more quickly after its violent birth than scientists once believed. These zircons are among the few surviving witnesses of Earth's earliest chapter, fragments that outlasted the destruction of entire continents. To hold a zircon under a microscope is to look directly into the dawn of Earth's history, a crystal memory of a time when the world was still forming its oceans, crust, and atmosphere. These ancient zircons record the first appearance of liquid water on Earth. Detailed analysis revealed chemical ratios consistent with rocks that had interacted with liquid water, pushing the timeline for Earth's oceans far earlier than once thought, perhaps within just 200 million years of the planet's formation. Before this discovery, scientists believed the young Earth remained a molten sphere for hundreds of millions of years. The zircons showed instead that the surface cooled rapidly enough to sustain rain, rivers, and oceans surprisingly soon. This realization reshaped our understanding of planetary habitability, suggesting that conditions suitable for life appeared quickly. Each zircon, smaller than a grain of sand, acts as a microscopic archive of water's arrival on Earth. Through them, we glimpse a world where vapor condensed, clouds formed, and the first drops of rain fell upon cooling rock, marking the beginning of the blue planet we know today. The continents themselves were once covered in lava fields the size of entire countries. Throughout deep time, enormous volcanic events known as flood basalt eruptions blanketed vast regions of Earth in thick sheets of molten rock. These outpourings sometimes continued for millions of years, forming plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan Traps in India and the Siberian Traps in Russia stand as dramatic examples. These eruptions released immense volumes of gas into the atmosphere, altering climate and ecosystems on a global scale. When the lava cooled, it left behind landscapes of stepped rock and mineral-rich soils that continue to shape agriculture today. To stand atop one of these regions is to stand upon frozen lava that once flowed like rivers of fire, rewriting continents and reshaping the planet's surface. These vast basalt fields remind us that Earth's calm present conceals a violent past when entire regions pulsed with magma and the air shimmered with volcanic light. Those lava floods have caused mass extinctions in the past. The largest volcanic outpourings did not merely reshape continents. They reshaped life itself. The gases and ash released during flood basalt events poisoned the air, darkened skies, and disrupted climate for thousands of years. The eruption of the Siberian Traps around 250 million years ago coincided with the greatest extinction in Earth's history, wiping out most marine species and many organisms on land. Massive releases of carbon dioxide and sulfur dioxide triggered acid rain, global warming, and ecosystem collapse. Yet even in the aftermath, new life eventually emerged, adapting to a transformed world. These cycles of destruction and renewal are woven deeply into Earth's story, reminders that even the most devastating events become foundations for what comes next. In every extinction lies the seed of evolution, a silent transformation written in ash and stone. Ash from ancient eruptions still lies buried within modern soils across the world. Thin layers of volcanic ash, preserved within sediment and soil, act as silent records of eruptions that occurred thousands or even millions of years ago. Each layer can be traced back to its source volcano through the unique chemical signature of its minerals, allowing scientists to match distant sites and build precise timelines of past events. Farmers often unknowingly work these ancient ashes into their fields, where their minerals enrich the soil with nutrients. In regions such as Italy, Iceland, and Japan, volcanic deposits have made the land extraordinarily fertile. To dig into such soil is to touch history itself, the residue of fire transformed into life. The same ash that once blotted out the sun now nourishes forests and crops, completing a cycle in which destruction feeds creation and catastrophe gives rise to growth. The Atlantic Ocean was once nothing more than a long rift valley. Before the ocean we know today existed, the land that would become Africa and the Americas was joined together in a single supercontinent. Around 200 million years ago, deep cracks opened between them, forming a vast rift that gradually filled with water as the continents drifted apart. Over millions of years, volcanic activity widened the gap, and a new ocean was born. The Mid-Atlantic Ridge, where new crust continues to form today, marks the original line of separation. Ancient rift valleys, such as those in East Africa, offer glimpses of what the early Atlantic once looked like. Long depressions scarred by fault lines and filled with rising magma. What is now a vast ocean began as a fracture in Earth's crust, proof that even the largest seas start as narrow wounds in stone. Today, the Atlantic spreads outward from the Mid-Atlantic Ridge like a slow conveyor belt. Beneath the waves lies a hidden mountain range where magma rises through cracks, cools, and pushes older rock aside in a steady, symmetrical flow, quietly reshaping the planet beneath the surface of the sea. As this process unfolds, the continents on either side of the ocean slowly drift farther apart, carried by the steady movement of the seafloor itself. What feels motionless on human timescales is, in reality, a powerful and persistent force reshaping the planet inch by inch. As molten lava rises along mid-ocean ridges and cools into new crust, magnetic minerals within that lava align themselves with the direction of Earth's magnetic field at the moment of their formation. These minerals lock in that orientation like tiny compasses frozen in stone, creating vast striped patterns across the ocean floor. Each stripe records a moment in Earth's magnetic history, including times when the planet's magnetic field reversed direction entirely. By carefully measuring and mapping these magnetic stripes, scientists were able to confirm that the seafloor is indeed spreading outward from mid-ocean ridges, providing decisive evidence for the theory of plate tectonics. Though the process advances at only a few centimeters per year, almost imperceptible in a lifetime, it is relentless and unstoppable. This immense underwater conveyor belt continuously creates new ocean crust while, elsewhere, older crust is dragged downward into the mantle at subduction zones, ensuring that Earth's surface remains in constant motion, alive with slow but powerful change. Along these same ridges, deep beneath the ocean's surface, hydrothermal vents give rise to towering structures known as black smokers. Seawater seeps down into the Earth's crust through fractures and fissures in the rock, descending kilometers below the seafloor until it comes into contact with intensely hot, molten rock. Heated to temperatures exceeding hundreds of degrees Celsius, the water becomes superheated and chemically transformed, dissolving metals and minerals from the surrounding rock. Buoyed by heat, it then rises rapidly back toward the ocean floor. When this mineral-rich water erupts into the near-freezing deep ocean, it cools almost instantly, causing dissolved compounds to precipitate out as dark, smoke-like clouds. These billowing plumes give black smokers their name. The vents act as underwater chimneys, continuously forming, collapsing, and rebuilding themselves. Around them, mounds of iron, sulfur, and other minerals accumulate, their surfaces faintly shimmering in the dim light. The surrounding water often appears to glow softly as particles reflect what little light exists in the abyss. In this extreme environment, a strange and resilient form of life thrives, feeding not on sunlight, but on chemistry. Each hydrothermal vent becomes a miniature world unto itself, a living reminder that even in eternal darkness, the planet finds ways to breathe, burn, and build. These vents support entire ecosystems completely independent of sunlight. Far beyond the reach of the sun's rays, dense colonies of life gather around deep-sea hydrothermal vents. Instead of photosynthesis, the foundation of these ecosystems is chemosynthesis, a process in which specialized bacteria convert chemical energy from substances like sulfur and methane into usable food. These microscopic organisms form the base of a food web that supports giant tube worms, clams, crabs, shrimp, and fish, creating communities unlike any other on Earth. Temperatures near the vents can swing dramatically, from near freezing seawater to over 300 degrees Celsius within just a few meters. Yet life not only survives these extremes, it flourishes. The discovery of these ecosystems in the 1970s permanently changed our understanding of biology, revealing that life does not require sunlight, only energy and water. This realization has profound implications beyond Earth, leading scientists to suspect that similar environments could exist beneath the icy shells of moons, such as Europa and Enceladus. What was once thought to be a barren, lifeless ocean floor is now known to hum with activity, powered by the planet's internal heat in an ongoing partnership between geology and biology. At these vent sites, minerals continue to accumulate, building chimneys that can grow taller than houses. Superheated fluids constantly deposit layer upon layer of sulfides and other minerals, gradually constructing towering columns that rise more than 20 meters above the seafloor. These structures grow as long as the vent remains active, forming intricate, cathedral-like shapes in the deep. Some eventually collapse under their own weight, only to be rebuilt again as mineral-rich fluids continue to flow. Within these formations, valuable metallic ores concentrate, the same kinds humans mine on land. Their shimmering surfaces host entire communities of microorganisms and animals, each finely adapted to intense heat and sharp chemical gradients. The vents pulse like underwater volcanoes, their chimneys smoking gently in the darkness, silent monuments to the creative power of pressure and heat. They stand as proof that even in the most extreme environments, Earth sculpts unexpected beauty far beyond human sight. Earth's magnetic field itself has flipped hundreds of times throughout the planet's long history. The magnetic poles have repeatedly reversed, with north becoming south and south becoming north. These reversals occur irregularly, sometimes separated by hundreds of thousands of years, other times by millions. The cause lies deep within the molten outer core, where swirling currents of liquid iron generate Earth's magnetic field. As these currents shift and reorganize, the field weakens, fragments, and eventually reestablishes itself in the opposite orientation. Evidence of these reversals is written into volcanic rocks on the seafloor, where iron minerals align with the magnetic field as lava cools. Each band of opposite polarity marks a distinct chapter in this ongoing cycle. Although a full reversal may take thousands of years to complete, life on Earth has persisted through every one of them without catastrophic consequence. These reversals remind us that even the invisible magnetic shield protecting Earth from cosmic radiation is dynamic, shaped by the restless motion of the planet's molten heart. During such reversals, compass needles would gradually point south instead of north. If you could stand on Earth during one of these periods, your compass would slowly begin to behave unpredictably. Over centuries, magnetic north would drift toward the equator and beyond, eventually pointing roughly south. These changes unfold gradually as the magnetic field weakens, splits into multiple poles, and finally settles into its reverse state. Rocks preserve the memory of these shifts, their magnetic minerals locked in the direction that was north at the time they formed. By studying these frozen orientations, scientists have reconstructed the timeline of reversals and tracked the wandering of the magnetic poles across the planet. Though the idea may seem unsettling, magnetic reversals are natural and frequent in Earth's history. They have never triggered mass extinctions or atmospheric collapse. Instead, they reveal the vitality of the geodynamo, the deep, unseen engine that keeps Earth's magnetic heart beating through time. Even today, the magnetic poles continue to wander. Earth's magnetic field is not fixed, and the North Magnetic Pole, once located in the Canadian Arctic, is now racing toward Siberia at a speed exceeding 30 kilometers per year. This drift reflects changes in the flow of molten iron within the outer core. As convection currents shift, they subtly alter the magnetic forces extending into space. Satellites continuously monitor these movements, updating navigation systems that depend on precise magnetic data. While magnetic north shifts, geographic north remains fixed, making the two distinct reference points. Most people never notice the difference, but to scientists, the wandering poles are a visible sign that the magnetic field protecting Earth's atmosphere is alive and evolving. The same invisible forces guiding compasses also reveal the slow, liquid heartbeat of the planet beneath our feet. The moon plays a crucial role in stabilizing Earth's wobble, shaping long-term geology and climate. Without the moon's steady gravitational influence, Earth's axial tilt could vary dramatically over time, swinging from nearly upright to extreme angles. Such instability would trigger chaotic climate shifts, transforming polar regions into tropics and back again. The moon's presence keeps Earth's tilt within a narrow, stable range, allowing long-term geological and biological cycles to unfold predictably. This stability supports consistent patterns in ocean currents, ice ages, and global weather systems. The tides generated by the moon's gravitational pull also help distribute energy through the oceans, influencing erosion and sediment movement along coastlines. Earth's balance between change and stability owes much to this silent companion in the sky. Every gentle tide, every rhythmic season, is partly a gift from the moon, which has guided Earth's motion for more than 4 billion years without interruption. Over vast stretches of time, lunar tides have sculpted coastlines, shaping the edges of continents grain by grain, leaving their mark across millennia. Each day, the ocean rises and falls in a slow, rhythmic motion as the moon's gravity reaches across space and gently tugs at Earth's vast bodies of water. This constant pull creates the tides, a daily breathing of the planet that has repeated without interruption for billions of years. Over years, centuries, and vast spans of geological time, these tides do far more than simply move waves back and forth. They quietly and persistently reshape entire coastlines. Tidal forces carve winding estuaries where rivers meet the sea, gradually widen bays, and transport immense quantities of sediment that build beaches, barrier islands, and fertile deltas. With every rise and fall, cliffs are slowly eroded, grains of sand are lifted and carried elsewhere, and nutrients are redistributed, sustaining rich marine ecosystems. In certain regions of the world, tidal ranges exceed 10 meters, exposing enormous intertidal zones that shift daily between land and sea. These ever-changing environments become nurseries for fish, feeding grounds for birds, and homes for countless invertebrates adapted to constant change. Over deep geological time, tides have influenced the formation of continental shelves themselves, shaping the margins of continents. This rhythm is ancient and unbroken, a direct link between distant celestial bodies and the fine patterns of sand beneath our feet. The shoreline we see today is not fixed, but a living sculpture, shaped grain by the patient, invisible breath of the moon. Coral reefs are among the most extraordinary living geological structures on Earth, built not by stone alone but by life itself. Though they teem with vibrant organisms, coral reefs are also monumental formations of limestone. Each tiny coral polyp secretes a calcium carbonate skeleton, and over countless generations these microscopic builders stack their structures upward toward sunlight. Over thousands and even millions of years, this slow accumulation creates reefs so vast they can be seen from space. The Great Barrier Reef, stretching more than 2,000 kilometers, was formed layer by living organisms no larger than a fingertip. When corals die, new colonies grow atop their remains, continuing the cycle without pause. These reefs act as natural breakwaters, protecting coastlines from erosion, while also serving as detailed archives of ocean history. Their layers record changes in temperature, chemistry, and sea level. Even fossilized reefs, now found far inland, tell stories of ancient seas that once covered modern continents. Every coral colony is both a thriving biological community and a geological monument, living rock that grows, breathes, and preserves the memory of the oceans that shaped our world. Some coral reefs are older than many of Earth's mountain ranges. Beneath the calm surfaces of tropical seas lie reef systems that have grown continuously for tens of millions of years, some originating when dinosaurs still walked the land. Over the same spans of time, entire mountain chains have risen, eroded, and vanished, while these underwater structures quietly expanded. Their cores are composed of compacted limestone formed from the skeletons of billions of tiny organisms. As sea levels rose and fell, reefs adapted by growing upward or migrating toward light. Today, fossilized reefs appear in deserts and atop mountain peaks, undeniable evidence that land and sea have traded places again and again. The endurance of coral reefs reveals the planet's continuity through upheaval. Their layered skeletons trace both biological evolution and geological transformation, standing as cathedrals of life and stone. Older than civilization, older than mountains, they are living bridges across the eras of Earth's unfolding story. Dust lifted from the world's great deserts can fertilize entire rainforests across oceans. Tiny grains of mineral dust rise into the atmosphere from arid regions and are carried thousands of kilometers by global wind patterns. Much of this dust eventually settles in distant ecosystems, delivering vital nutrients. The Amazon rainforest, for example, relies on phosphorus-rich dust blown from the Sahara Desert each year to replenish its soils. Without this steady supply, heavy tropical rains would wash essential minerals away. Satellite imagery has revealed vast plumes of dust crossing the Atlantic Ocean, glowing softly in sunlight before falling as invisible nourishment. Each grain is a geological traveler, a fragment of ancient rock that left one landscape to sustain another. In this quiet planetary exchange, deserts and rainforests become partners in a global cycle of erosion, wind, and renewal that connects distant environments into a single system. Rocks on Earth also contain tiny fragments of stardust, linking geology directly to the cosmos. Within certain meteorites and even ancient terrestrial rocks lie microscopic grains that formed inside dying stars long before the solar system existed. These particles survived the violent collapse of the gas cloud that birthed the sun and became incorporated into the material that formed planets. Their isotopic signatures differ from anything produced on Earth, marking them as truly extraterrestrial. When scientists isolate these grains, they can reconstruct the life cycles of stars, from formation to explosive death. Each speck carries atoms forged in stellar furnaces, proof that all matter on Earth was once part of distant suns. These fragments bridge time and space, reminding us that geology is not limited to our planet, but part of a universal story of matter endlessly transforming. Gold and platinum also arrived from space. During Earth's formation, nearly all heavy elements sank into the molten core. The precious metals we mine today were delivered later by meteorites during a period of intense bombardment more than 4 billion years ago. These impacts scattered metallic debris across the surface, enriching the crust with materials forged in stellar explosions. Every gold vein and platinum deposit is a cosmic inheritance, the residue of celestial violence. To hold gold is to touch the memory of ancient star death preserved in stone. Some impact craters have been eroded almost beyond recognition. Over millions of years, wind, water, and tectonic forces soften rims, fill depressions, and bury scars beneath forests or seas. Yet traces remain in shocked quartz, melted minerals, and fractured rock. Using satellites and magnetic surveys, scientists uncover these hidden wounds across continents. Their near invisibility shows how Earth heals itself, slowly smoothing even the deepest injuries. One colossal impact may have reshaped life itself. Around 200 million years ago, a massive asteroid likely struck near modern Canada, coinciding with an extinction event that reshaped ecosystems. Skies darkened, wildfires spread, climates shifted, and dinosaurs rose to dominance. Another impact, 66 million years ago, ended their reign when an asteroid struck the Yucatan Peninsula, releasing energy equal to billions of atomic bombs. The impact was so immense that it instantly vaporized solid rock, ignited wildfires across entire continents, and hurled unimaginable quantities of dust, ash, and debris high into the atmosphere. For years afterward, sunlight struggled to reach the surface. Skies dimmed, temperatures fell, and photosynthesis collapsed almost entirely. Plants withered, food chains unraveled, and ecosystems that had flourished for millions of years fell silent. More than 70% of all species vanished from the planet, including the non-avian dinosaurs that had ruled the land for over 100 million years. The crater left behind by that collision, known as Chicxulub, remains buried beneath thick layers of limestone in what is now the Yucatan Peninsula. Though hidden from view, its circular shape is astonishingly well preserved. Beneath its rim lie rocks fractured by immense pressure, minerals altered by extreme heat, and melted material that cooled in seconds. These layers form a frozen record of one of the most violent moments in Earth's history, a scar sealed beneath stone. Yet from this devastation came renewal. With the dinosaurs gone, mammals emerged from the shadows, adapting, diversifying, and slowly rising to fill newly opened ecological niches. Over millions of years, this shift reshaped life on Earth and eventually led to the appearance of humans. The event that ended one age also began another, demonstrating that destruction and creation are inseparable threads in the planet's endlessly turning cycle of change. Earth's surface is dotted with hidden scars left behind by ancient cosmic collisions. While some impact craters remain visible today, many others lie buried beneath oceans, deserts, forests, or younger layers of rock. Geologists uncover them by detecting subtle gravitational and magnetic anomalies that hint at circular structures concealed deep below. Some of these scars are so old they date back to the planet's earliest eons, a time when Earth endured relentless bombardment from space. Those impacts reshaped the crust and may have delivered much of the water and carbon essential for life itself. Though hidden, these scars form part of the foundation beneath our feet, silent evidence of a turbulent cosmic youth. Over immense spans of time, erosion and plate tectonics softened and erased many of these marks. Mountains rose and fell, oceans opened and closed, and continents drifted away from their ancient wounds. Yet deep within the rock, the memory remains, waiting patiently to be read by those who know how to listen to stone. Even today, Earth continues to receive material from space. Every single day, hundreds of tons of microscopic cosmic dust drift into the atmosphere. Some burn briefly as meteors, flashing across the night sky, while others settle quietly onto land and sea, unseen. Scientists estimate that more than 100 tons of this interplanetary material accumulate daily, most of it shed by comets and asteroids as they circle the sun. Researchers collect these particles in Antarctica, on rooftops, and in remote regions, where tiny metallic spheres glint beneath microscopes. Over billions of years, this steady accumulation has subtly increased Earth's mass, even as erosion and escaping gases slowly remove material. It is a gentle, ceaseless rain of stars, reminding us that the planet remains connected to the wider cosmos. Geology links every mountain, ocean, fossil, and living thing into one continuous story. Nothing exists in isolation. The same forces that lift mountain ranges also stir the seas, recycle rocks, and shape the conditions for life. Fossils reveal how shifting climates and moving continents guided evolution, while minerals record the deep processes that sculpted the planet from within. Every river carries the memory of erosion, and every grain of sand was once part of solid stone. Over billions of years, plate movement, volcanism, and weathering have woven together an unbroken narrative connecting land, life, and time itself. Geology is the language of that story, written in layers beneath our feet. It reminds us that the world is both ancient and alive, endlessly changing yet profoundly patient. To study the Earth is to read the autobiography of the planet itself. The rocks beneath us are the planet's memory written in stone. Every pebble, cliff, and mountain is a page in Earth's vast diary. Within their grains lie records of ancient seas, fiery eruptions, glacial ages, and the slow drifting of continents. Radiometric clocks measure their ages, while fossils and mineral patterns reveal the climates and creatures that came before us. Rocks remember pressure and heat, flood and drought, creation and decay. Together, they form the grand archive of time. Standing on solid ground feels like permanence, but in truth we stand atop history in motion. The crust is forever forming, breaking, and reforming. To listen to the Earth is to hear its long, quiet memory, the murmuring of stone recording a world that has never stopped changing, growing, and remembering itself. Even now, as you rest, the ground beneath you moves slowly beneath stars that once forged the minerals in your bones. Deep below, molten rock flows in endless cycles, shaping continents that drift like slow clouds across a sea of stone. Geology reminds us that change does not always roar. Most of it whispers. Mountains rise grain by grain. Oceans widen beyond memory. Every pebble, every crystal, every grain of sand carries time so vast that our own lives seem like brief flashes of light. Yet even those flashes belong to the same pattern written into the fabric of the planet. Somewhere deep within Earth, pressure builds. Somewhere else, it eases, and a new rock begins its long transformation. Far above, wind grinds stone into dust, and that dust drifts across oceans to feed life. Everything that ever was becomes something new again. The planet breathes in the slow rhythm of stone, and we breathe with it, often without knowing. As you drift towards sleep, imagine that deep pulse beneath you, ancient and steady. Let it quiet your thoughts and slow your breathing. You are part of this story, too. A brief moment in a vast, unfolding world that remembers everything. For now, simply rest. Let the planet cradle your thoughts. Patient, eternal. Sleep well and good night.